All right, hi everyone. This is a video solution for homework 5, question number 1. And in this problem, we're given this assembly of multiple pulleys. We've got some pulleys that are pinned, and we have some pulleys that are in a horizontal track. And we are asked to find one unknown. What is the vertical reaction at A? So this scribble is here. So we are looking to solve A sub Y. That's what we're asked to do. And man, just like everything else in statics, we are going to focus on our free body diagrams. And you can need multiple free bodies in order to solve this one. So I'm going to start and turn down the tone on that. I'm going to come over here to node A. I trace the pulley. So I'm going to keep the pulley sheave. I'm going to take out the bolt. So I keep the hole. I'm going to keep the cable. And I'm going to cut through it. So cut, cut. When I cut through the cable, I expose the internal tension force, and I'll just use a capital T for that unknown. We know that when friction is not taken into account, right, then tension is constant in a cable that is draped over different pulleys. And to put this in equilibrium, I just need the force in the y direction at A. So I'm going to need a vertical force here. That's A sub y. That's what I want to solve for. And that vector represents the push of the bolt on the inside of the pulley wheel. That's what's been removed from the picture here. So our first equation, summation of forces in the y direction equals 0. That's going to let us deduce that 2t is equal to ay. So now we know all we have to do, if we can solve for t, we're going to be able to solve for our unknown a sub y. We're done with that free body. That one's not going to help us anymore, so I'm going to turn that one off. And remind you that in a pulley system, just a second, I forgot that I could turn my symmetry on for this and make my life slightly easier. In a pulley system, think of this cable as one length of rope or steel rope or wire or whatever this is, right? But it's anchored down here. It goes up through a hole in that weight. It's draped over a pulley. That pulley changes the direction, but it doesn't change the intensity, the force. So this is just one piece of cable draped over different things, but the amount of tension in it has to be constant. So anywhere we cut through those cables, we know we're going to get that unknown tension force. Well, the fastest way to solve this problem for the second free body, it looks something like this. And if you did this, you are pretty much a statics rock star. So this free body is appealing to me. I want to disconnect as few things as possible because every time I disconnect something, I have to introduce more unknowns. But if I just grab this much of my structure, then in order to create this free body, all I have done is cut the cable 1, 2, 3, 4 times. And so I have 1, 2, 3, 4 tension forces. So I can solve for that very quickly. Summation of forces in the y direction equals 0. Going up, I have 4t. Count them up, 1, 2, 3, 4. And all the weights going down, that's going to sum up to 1,000 newtons. And then my tension force is going to be equal to 250. We can take that 250 newtons and then plug it back into this equation to get to the answer really quickly. Okay, so A sub y 2 times 250 equals 500 newtons upwards. Okay, so that's our final answer. Now, the question that you may have is, what about that spring? Why is this a legal move? I don't have any idea how much force is in that spring. Well, because you didn't detach it, you don't have to put a force there. There's a lot of power in being clever about where you make your free body diagrams. Now, that said, this is one way to solve the problem, but they're not always this easy. I'm going to show you one other good technique, way to check your work, that's kind of broadly applicable to other problems, and it would go something like this. So I'm going to do this free body. I'm going to detach the spring and that free body, and then while I'm thinking about it, I'm going to do one other one down here at the bottom. So cut, disconnect, cut. Okay, so that's my other free body. And both of these are separate free bodies, and there's some things that they have in common. So I can do my cut plane, cut plane. I can do my tension force, and I gotta watch my layers. Something that's all messed up. All right, this one, tension force, and the lower free body got the same tension force. The only difference here is that now, since I've disconnected the spring, I do have to make an assumption for whether it's in tension or compression, and then just be consistent with that. And I'm just going to arbitrarily assume it's in compression. Okay. Maybe I can deduce, maybe I'm making a theory. What I want to show you is that the math, it's not in compression, it'll end up being in tension, but let's just pretend that we think it is in compression and we'll just see how that math works out. So if I'm assuming it's in compression, for this top body, that means arrow toward the body, and I'll just call that S as my spring force. And let's go to the other free body. So arrow toward the body. There's my compression, assumed an S for my spring force. And now I have both of these free bodies are complete, ready to go. And as I pull them apart, that just gives me a chance to think more about Newton's third law. And if I wanted a free body even of that spring in and of itself, right? So if I did a different free body, let's get one more, just because I'm kind of going into teaching mode. And so if I pulled the spring out, like where is that compressive assumption? It looks like this, right? So that's the spring force, S. Okay. And in all three of these free bodies, they're all valid free bodies, and they're all showing the same thing, arrows toward the body, compression traveling through that system. Now, where are the Newton's third law pairs? Well, these are the Newton's third law pairs, and these are the Newton's third law pairs. Okay, that's what's happening at that point in space. All right. I think we're ready to write some equations. So I'm going to do a new layer and maybe just zoom in, and let's finish this one off. So for the top free body, I need a summation of forces in the y direction equals 0. Upward, I have 2t plus s. And downward, I have 300 newtons. And just kind of thinking ahead, I'm going to rearrange this 300 newtons minus 2t. And that's the only equation I can write from my equations of equilibrium. And I do have two unknowns, S and T. So let's go down to the next free body. Come down to this one here. I'll change colors. I'll make this one purple. All right, so for this one down here, summation of forces in the y direction equals 0. For this free body, upward I have 2t, and downward I have the spring force plus 700. And I am ready to do my final solution because again, I've got two unknowns and two equations. So I'm going to use substitution or elimination, and I've set this up so that this is ready to be substituted here. So let's write that out. 2t equals 300 minus 2t plus 700. 500. Rearrange 2T equals 1,000 newtons. Therefore, tension is 250 newtons. And with that information in mind, we could go back and get the correct answer to the problem. Up here, I plug it in just like we did earlier. Now, this particular problem didn't ask us to solve for the spring force, but let's pretend that it did. Oops, wrong layer. Let's see, spring. Okay, we're going to pretend that the problem's asking us to solve for the spring force. And we assumed compression. Let's go ahead and calculate it, and a positive sign will validate the assumption, a negative sign will reverse that. So I'm going to plug into this equation. So we'll do the spring force is equal to 300 minus twice the tension force, and plug that in right there. 300 minus 500. Therefore, my spring force equals negative 200 newtons. Okay, and this gives us a chance to make our final answer, like if we were asked about the spring force, so we'd say spring force is negative 200 newtons of compression, therefore 200 newtons of tension. And just express our final answer. That's the end of this one. Hope you enjoyed. Thanks for watching.